All right. Hello everyone. Let's get started. Today, it's our great honor to have Professor Bhaskar Krishnamachari from USC to give us a talk titled "Decentralized and Dispersed Computing for the Internet of Things." Let me give a brief introduction of Professor Krishnamachari. Uh, uh, Professor Krishnamachari is currently a full professor of electrical and computer engineering at the USC Viterbi School of Engineering. He is one of the leading scholars actually in the domain of mobile computing, Internet of Things, and blockchains. His research spans the design and evaluation of algorithms and protocols for wireless networks, distributed systems, and the Internet of Things. And he's the prolific scholar, and he is the author and co-author of more than 300 technical papers, 3 books, and which have been collectively cited by more than 34,000 times. He has co-authored papers that have received many awards, including the Best Paper Awards from ACM IPSN, ACM Mobicom, and IEEE VNC. And he's the IEEE fellow. So without further ado, let's give the floor to Professor Krishnamachari.
Thank you, Me, for the kind invitation and the introduction. So today I'm going to give a talk about some work we've been doing, maybe about over the past 5 or 6 years, looking at decentralized and dispersed computing for the Internet of Things. So let me kind of define these terms a little bit, just so that we're all on the same page. So when I'm talking about decentralized computing, really I'm focusing on the use of blockchain technology and related methods to enable the operation of distributed systems that cross administrative, economic, and trust boundaries. And with these systems, one thing that changes is that not only can you communicate and process data, you can also communicate and process economic value, and you can build richer systems because you can combine these ideas of data and economic value. I will also talk about in the second half of the talk about something called dispersed computing, which is really about deploying and executing complex applications. Often these are some kind of a task graph of sensor processing tasks that can be executed in a concurrent manner over a networked distributed computing environment with heterogeneity and dynamics. So let me start with decentralized computing first. So, when a lot of people hear about blockchain for the first time, perhaps it's in the context of something like Bitcoin, and they're thinking primarily of cryptocurrencies, which are the, sort of these decentralized currencies. And while that's certainly how the field got started, people realized very quickly that the underlying technology was inherently a way to create tamper-proof data storage, so decentralized ledgers and a number of applications that you can have if you have tamper-proof data, for exchanging data and value in ways that are more give you higher integrity and availability and transparency in some cases. So then there's sort of another stage in the evolution where people realize, well, not only can we move value and store state, we can also do computations over that state and combine those computations with the storage and movement of monetary value. And this brings us to kind of the third circle here of decentralized computation. And by far the most well-known decentralized computation system on the blockchain is the use of the Ethereum virtual machine on the Ethereum blockchain, where you can write what are called smart contracts using a programming language called Solidity and deploy them on chain. And it essentially has data that's stored on chain that's used in the computations. The state itself is stored on chain. It can, run through instructions that are sent as transactions and produce outputs that change the state on chain of the smart contract and possibly of the movement of some underlying cryptocurrency. And the reason that this is really a fascinating space is that over the past, I would say at least a decade, of work on decentralized computation, a number of different kind of layers have emerged. So the base layer, we've got a lot of cryptographic building blocks, from public key cryptography to hashing Merkle trees, digital signatures. More recently, there's a lot of exciting development happening in what are called zero knowledge proofs, which give you both high levels of privacy and verifiability for computation that is done off chain, but you're putting proofs on chain. And then above this, there's always been a lot of work on various types of what are called Sybil control mechanisms for permissionless blockchains, as well as permissioned systems. Above that, of course, lots of different consensus mechanisms that people work on. Above that, how you're trying to represent the data. Is it as a chain actually of blocks, or is it a more general, directed acyclic graph structure? Above that, there's been a lot of development and protocols that find ways to make blockchain systems more scalable, support larger numbers of transactions per second, handle large amounts of computation on chain. And given all of this infrastructure, we can do some very interesting decentralized computing on top. And I'll show you an example today that pertains to paying for IoT data, for example, or digital data in general. And above this, of course, the applications of blockchain. We are largely hearing about lots of applications to decentralized finance. More recently, in the context of the election, there was a prediction market on a blockchain platform called Polymarket that was also in the news for predicting the outcome of the recent election, maybe months in advance, or at least weeks. But there's also interesting applications for blockchain that are still being figured out in the world of business supply chains, and I'll argue for the Internet of Things, and many other use cases. So a question I often get asked is, why are you doing academic research in this space, right? Isn't blockchain technology just for people with a Coinbase account to do some speculation on cryptocurrencies? What's the research value of this field? I actually think this is an exciting green field. There's a lot of open questions. Most of the work happening in this field is by industry practitioners that, for lack of a better word, are essentially doing this kind of making sort of designs that are single points in a large design space. And so they come up with something, but often the new idea that is in a particular protocol has not been rigorously verified. There's not a lot of good theoretical framing of it. There isn't a way of kind of generalizing what they've done and systematizing it, identifying other points in the design space, and so on. So there's a lot of interesting work you could do, just sort of understanding what the current state of the art is, and then bringing academic rigor to that. So there's a lot of room for new algorithms at every layer of the blockchain stack, all the way from the consensus mechanisms to new types of smart contracts and more. Definitely for people that are more on the application side of things, trying to identify ways in which you can incorporate the new capabilities of trust and privacy and transparency and security that you get with blockchain systems in the context of the application. So how do they fit as a building block, and how do they enable something new that wasn't possible in a given application domain? So whether it's IoT or even for IoT in a particular setting, whether it's application to healthcare, application to precision agriculture, etc. There's a lot of interest in this space in being able to do some analysis and provide provable guarantees. There's a lot of, the space is projects that are advertising certain capabilities, but that haven't been academically rigorously evaluated. And so, providing whether they are, pen and paper theorem proof type of guarantees or empirical evaluations, there's a lot of room for academics to contribute there. And ultimately, the whole space is in need of research to provide improvements in efficiency, scalability, sustainability of the technology. And so there's a lot of open problems that academics can work on. And so, I do want to take the time to suggest that for PhD students, faculty looking for new rich areas for exploration with a CS background, computer engineering, electrical engineering background, I think there's a lot of interesting things here, and a lot of, I would say, relatively lower hanging fruit compared to many other fields. Also mentioned briefly here, there's a lot of room for interdisciplinary collaborations here as well, because blockchain can touch across topics like finance, sometimes law, There's a lot of conversations that happen in the field that expose you to ideas outside of just engineering, and I think that that's often a plus as well. So I want to give you a few examples of research that we've done somehow at the intersection of blockchain and IoT. The first of these is a consensus protocol that is suitable to involve mobile devices called Blizzard. Another one is a way of connecting MQTT or other decentralized pub subsystems with the blockchain called Trinity. And then I want to talk a little bit about some interesting problems when it comes to paying for IoT data when the data crosses economic boundaries. So the work on Blizzard that is described here was really motivated by the observation that today's blockchain systems largely rely on online servers. These servers have to be connected to the internet 24/7. They have to be quite powerful. And as a result, a typical, even a large blockchain system might have hundreds of thousands of servers participate in it. But we're kind of leaving on the floor, if you will, the billions, literally, of mobile devices that people have around the planet that have computational capability. And the way blockchain systems work, the more devices are involved in the validation of transactions, the more security you're providing to the system. And also, if you can, allow mobile devices to participate in validation of transactions, and they can be given some compensation for their participation, it might also help kind of scale up the technology and bring it to more people kind of that are participants in the ecosystem itself. So for all these reasons, we were interested in exploring, what would it take to do that. But there are some challenges. The biggest challenge is that mobile devices, unlike online servers, by definition, are not always online. You might be turned off for sleep, you might be out of some coverage range, your bandwidth might be fluctuating and dynamic. And so there's a lot of kind of connectivity issues with mobile devices that you don't have in the typical blockchain systems. Also, of course, your mobile device is going to be relatively more limited, certainly for storage, but also even potentially for computation. Although I would argue that today your average mobile device is computationally quite capable if you compare it to even desktops some years ago. So one issue here is that because these nodes are not always online, we need to have an architecture. And what we proposed here in our protocol called Blizzard is a two-tier architecture where we do have online brokers that are on all the time. And the mobile devices essentially are matched randomly to subsets of the brokers at each kind of time step. And the protocol that we came up with, Blizzard, is built on top of an earlier protocol called Avalanche. It's part of a blockchain system that's already deployed out there that does gossip-based consensus. Now, in Avalanche, every node randomly picks some other node that's an online server to be able to connect with and send messages. Mobile devices can't arbitrarily contact other mobile devices because you wouldn't, have a directory structure that's got, millions of entries in it to pick randomly. Plus, as we said before, nodes may or may not be available at a given moment in time. So instead, in our architecture, the mobile nodes will communicate with brokers. The brokers will aggregate what they're hearing from multiple mobile nodes and transmit the information back to the nodes that are connected to them. And so long as this bipartite graph has enough connectivity, you can actually sort of communicate and achieve consensus by kind of waves of this up and down communication over a few steps. You basically get the entire network essentially will be able to arrive at some consensus about a given transaction. One kind of building block that we had to come up with for the system is to prevent collusion. So it turns out that if mobile nodes could decide which broker to connect to, a malicious adversary might design a matching such that certain mobile devices are connected to certain colluding brokers in such a way that the consensus is steered in the wrong direction. And to kind of minimize or prevent that, we want the matching at each time step to be truly random. And this uses basically a distributed random beacon and a way to kind of provide this random matching and a guarantee that you're not connecting with an adversarial choice that you have made yourself. It's something that is out of the control of the adversary. often with consensus protocols for the blockchain, you have to prove certain properties, in particular of having to do with safety, that under certain assumptions about how many of the brokers can be Byzantine or how many of the nodes can behave in a Byzantine fashion, you want to be able to show that the consensus is not prevented to arrive at the correct solution. And what's interesting in our system here is that it's not just the brokers or just one set of servers. We have two classes of nodes. We have the mobile nodes and the online brokers. And so we show that the safety region for this protocol is really described by a two-dimensional region. So long as the number of adversaries that have taken over brokers and the number of or the number of brokers that have been taken over by adversaries, or the number of mobile nodes taken over by adversaries, stays within what's shown here at the yellow region, we can mathematically prove that the system will be safe and correct and achieve good consensus. And this is kind of a two-dimensional generalization of traditional ways of reasoning about consensus protocols under Byzantine adversaries, where you typically have one dimension and you say so long as no more than 50% of the brokers are Byzantine, we can achieve consensus, or a third or so on. So here we're getting a two-dimensional region. We also, in our work, developed a very general way to analyze the throughput and latency, not just of our consensus protocol, but in a framework that can be applied to other consensus mechanisms. Essentially, for every transaction, from the moment a node proposes it to the moment it becomes finalized and logged in the ledger, you can kind of identify all of the steps that are involved, and they're a combination of communication steps and computation steps. So for our particular protocol, the orange blocks here are computation steps, and the green blocks happen to be communication steps. And so if you can kind of describe your protocol from the perspective of a transaction as to the series of computations and communications it involves, you end up with kind of this linear chain of processes, if you will. And what is nice about this formalism is that now, if you simply added up the time it takes for each of those steps for computation and communication, you can quantify the end-to-end latency of transaction confirmation. And if you identify the bottleneck time here, in other words, which of these is the largest, and you take the inverse of that, that tells you about the throughput of your protocol. So it's sort of a nice way to unify the analysis of throughput and latency of many, many consensus protocols that more or less fit this framework. So that was another contribution of the work. And finally, we actually did some performance evaluations. We showed that this Blizzard algorithm, the kinds of computations it needs, are such that on a typical state-of-the-art mobile device, you would be expending about 0.1 millijoules per transaction, and completes in about 100 microseconds. And that with this type of capability, you can afford to have about 10,000 transactions per second as a throughput. The end-to-end latency is under a second, and this is competitive with the best state-of-the-art kind of current generation blockchain systems out there. And what's nice about this system is that you can have many more shards than a typical blockchain for the same security, just because the sheer number of nodes available to you might be now scaled by several orders of magnitude. And so it can really scale your overall scalability dramatically. So I'll move to another project now. So this is looking at something that's very common in Internet of Things systems, which is having a pub subsystem to disseminate your data. You have a set of publishers and subscribers and brokers somewhere that are mediating between the data that's being published and that subscribers are subscribing to. They're very popular for IoT applications because they really help scale the system so that not every source of data needs to know who is interested in my data. So I don't have to have a bunch of end-to-end flows between the source of data and the consumers of the data. I just push all my data to one location, which is the broker, and whoever is interested in that data can simply ask that broker and subscribe to the data, and sort of makes it easier for a wider number or range of subscribers to connect to a set of sources in an IoT setting. These subscribers could be end viewers, it could be a dashboard, it could be algorithms that are computing something based on the raw data. It might be control mechanisms that are acting on that data. And so it sort of facilitates an easy connection between the publishing and the subscribing. But when you look at all of the state-of-the-art pub/sub mechanisms, by and large, they are centralized in the sense that that broker is typically a single node or at least a single organization that is running the broker. And they offer various levels of crash tolerance, within that single organization structure. But they typically don't handle Byzantine faults. So it's one thing to say your server goes down, you just have to reboot it. But a Byzantine fault is somebody has taken over your server and is manipulating, for example, and censoring which subscribers see what information in what order, or even feeding fake data to certain subscribers, right? So that's a completely different failure mode than just saying your server went down and you have to have some backups available for it. So we thought of using blockchain systems to handle these issues. So provide crash tolerance, Byzantine fault tolerance, and allow the brokers to be hosted by multiple organizations. Now, the reason for this, to some extent, is a question of trust. So kind of if your IoT application is simple enough, everything stays within an organization. Whoever's hosting the broker you trust, all is good. But as you want to deploy this to very different applications, maybe in a city scale, you run into some trust issues. Whoever is running the broker may have an incentive to prevent certain parties from seeing the full data, may have an incentive to change the order of the data, and so on. And so, if there are multiple different organizations involved, they want to have some trust in the process. If they could each have a copy of the broker that are combined together in a consensus mechanism to make sure this doesn't happen, then you have more kind of integrity in the system. So that's the basic idea here is we take a bunch of different administrative domains, each of which runs its own broker and runs a consensus node on a blockchain protocol. In our implementation, the broker is just an MQTT broker, and a blockchain node is a Tendermint instance, which turns out to be cheap and simple and lightweight enough to run even on a Raspberry Pi. And the actual kind of blockchain part of it, the distributed ledger layer, is kind of optional, whether or not you want to store the messages that were sent, in a persistent storage that's immutable. That's maybe an option you can turn on or off. But nonetheless, having that consensus between the brokers as to which messages are confirmed to be valid and the ordering of the messages being consistent across all the correct brokers. This is something that the Trinity system that we have can guarantee. And we actually provide a theoretical analysis of the system and do this implementation with MQTT and Tendermint. And we show that indeed, it is able to provide these guarantees that whatever any subscriber is seeing, the particular messages, the order in which those messages are sent, is exactly what every other correct subscriber will see in the system, so long as your number of Byzantine nodes is no more than a third of all the brokers and consensus nodes that you have in the system. And we also measured empirically with our implementation on Raspberry Pi what is the cost of gaining this trust. And you can see in the x-axis here the number of nodes participating in the consensus and hosting of the broker, and on the y-axis the delay that it takes for any message from a publisher to reach the subscriber. And you see that there is an overhead. There's a cost we're paying in terms of more processing delay for doing the consensus, but it's largely linear. And so if you want more trust, you have more nodes involved in the consensus process, you're paying kind of proportionally more in terms of the delay of receiving each message. And so for applications where at least some of the messages need that additional level of trust, you might want to have more brokers involved, and perhaps other best effort or less trust requiring data could just go directly with a single broker. So this is our work on Trinity. So the third thing I want to touch on with respect to blockchain is paying for IoT data. And here, kind of the motivation again is when your IoT data is within the same organization, we don't think about paying for it, right? It's my data, I can consume it wherever I want. But the moment, again, I think about doing something at a large scale, and we had a project at USC developing something called I3, an IoT system for smart cities. We found that different private and public entities own different sources of data and IoT devices, and the consuming application or user organization doesn't necessarily own the data. So they have to enter into some agreements with the data providers. And sometimes they'd be willing to share it out of the goodness of their heart because they want the community to prosper. But more often than not, they need an incentive to actually share the data. And often monetary incentives are a big way to collect that data. And not only that, the moment you can set up an ecosystem where payments are part of the value for the data an IoT device produces, it also incentivizes companies and private entities to deploy more useful sensors in a city to actually create this ecosystem around a smart city. And so enabling and facilitating payment between organizations for IoT data can be really helpful. Now, to give you an idea of why this is not a trivial problem, if you think about your average experience going to a news website to try and see an article, you'll find that most of them are paywalled. Most of them want you to subscribe to that newspaper before they let you read more than, say, 3 articles a month. And part of the reason this happens is that today's internet has a very high friction for setting up payment for data. You pretty much have to have an account with that particular provider. That account has to be a credit card, thing that you set up. They also want, there's a secondary issue. They want your loyalty. So they're trying to lock you into being their subscriber and so on. But it's a very painful process. So imagine a world in which your browser automatically deducted, I don't know, 5 cents for every time you read the article on a particular news site without your even expending any, brain cells in making sure you can do that. And no matter which provider you went to, you're able to do that. And so there is an economic value happening, economic interaction happening. I think this would go a long way to reducing that friction. But the problem is, it has to be something that gets really almost built into the application layer or the transport layer of the internet rather than having to be re-implemented with third-party providers. So we proposed an idea that we call the streaming data payment protocol, which in addition to the traditional TLS and TCP layer to move data between a client and server, also allows for the entire economic interaction to be handled automatically. So, a client which is interested in buying the data would approach a server. The server would provide a menu of data items it has available for sale. The client could place an order for some data. It could get the data. It could make a payment for the data. It would get an invoice for the data. Get an invoice for the data, make a payment, get an acknowledgement of the payment, have receipts, and the payments themselves would go through some kind of a payment channel. Now, it could be a cryptocurrency channel, as we were advocating, but it doesn't have to be. It could even be something like Stripe or some existing payment rail that are kind of Web 2 mechanisms. But also use a distributed ledger, an immutable ledger that's decentralized to keep records of these transactions in case there's any disputes or if you need access to that for your commercial purposes. So the idea is to kind of package all of this as a protocol that every browser more or less would just have under the hood. Every IoT client server protocol could just incorporate, and without having to reinvent that wheel over and over again. And so by kind of turning it into this low friction interaction, because it's sort of subsumed inside a protocol, we think you would dramatically increase the lower the friction for moving data. And so, we did some evaluation. So one thing we did in this implementation is, now if the buyer pays for just one unit of data and he gets it, and the next unit of data has to make a payment again, it's going to slow down. It's going to introduce some delay or interruption in the process. And so you might want to say like, oh, maybe I'll pay for K units of data. So this K becomes a parameter that, as that K is smaller, you have a kind of, more interruptions because you have to keep paying before the next unit of data arrives. But on the other hand, if K is large, which makes this process smoother, you run into the issue that if the buyer has paid for K units of data and the seller stops providing the data, that they paid more than they actually got. Or even in the other direction, you could also set it up so that the seller will be willing to advance you K units of data for each payment. But the larger that K becomes, the more at risk the seller might be in this case. So there's kind of a risk at either the buyer end or the seller end as the K gets larger. And we showed, in fact, that it is lower latency, lower friction for higher K, but we're dealing with this higher financial risk on either party. So SDPP doesn't quite solve this problem. It just has a parameter and you get to choose it. But we got to thinking about, is there an actual solution for this problem so that neither the buyer or seller have to be worried about getting cheated? And we came up with a solution for this is kind of a well-known problem called the buyer and seller's dilemma. And we showed that, in fact, there is a solution that can be implemented using a smart contract on blockchain to address the fear that both the buyer and seller have that they might be cheated, right? So imagine that you go to buy a PDF file from someone you don't know on the internet, and they email you saying, "Hey, would you like to buy this digital book?" And you say yes, and they say, "Go ahead, make me the payment, and I'll send you, the PDF." You make the payment, and then they could just disappear without sending you the book. Or in the other direction, the next time you're wiser and you say, "You know what, send me the PDF before I make you the payment," they send you the PDF, and of course you're using a burner account and you disappear without making the payment. So the inability to trust the other party ends up blocking peer-to-peer digital transactions in an anonymous kind of online permissionless setting. So what we propose as a solution for this is a dual deposit or double deposit escrow, in which before the actual movement of the digital good happens, both the buyer and seller first have to put in a deposit that's a security deposit. Now, we're all familiar with security deposits. Every time you go to rent a car or rent a hotel room, they put in like a little deposit from you. Those are single deposit escrows because you're not worried about the hotel disappearing or the rental car disappearing on you, but they are worried about you doing that to them, right? But in this case, since both parties are worried about the other party, they both have to put in a deposit. Now, in an ordinary, store setting, this makes no sense. Like, what would it mean for me to give you $100 and for you to give me $100 as deposit? Because we haven't done anything, right? We've just canceled each other's deposit out. Or we might invoke a third party individual and give them our deposit, and we have to trust that this third party really will be fair and unbiased. And in fact, some early blockchain online marketplaces, there's one called OpenBazaar, did exactly that. It would involve a third party chosen at random to serve as a kind of a judge or a mutual trusted escrow. But we showed that you don't have to do that. We could simply create a script, a smart contract to which the funds are deposited, and it algorithmically will only release this deposit under the situation that the seller has provided the good and the buyer approves. And we do kind of a description of the protocol, and you can analyze it using game theory, using a game tree, where you think about, should the seller cheat the buyer, should the buyer cheat the seller, or what are all the different possibilities. And you can show that there's only one sub-game perfect Nash equilibrium, and that's achieved by a strategy profile where both the buyer and seller are actually honest with each other. So in fact, having this double deposit escrow is provably the right thing to do if both buyer and seller are rational. One interesting open problem is that it doesn't solve the problem when either the buyer or seller is not rational but malicious. So if they're just out to get you, they can force you to lock your deposit and never get it back, even at a cost to themselves, because they're malicious. They really don't care about hurting themselves. They just really want to hurt you. Now, the one way you can defend against that is to make the escrow amount even larger. So the amount that they're going to damage themselves is so high that might be a deterrent. But then it causes a lot of friction in the exchange of the digital good, because you don't want to be putting $1,000 deposit on a $10 book that you're going to buy, right? So that is an open problem still as to whether that's even possible. Is there a mechanism that you can do to bring down the friction while still deterring malicious buyers or sellers from hurting the other party? Okay, so these are sort of a few illustrations of where blockchain can interact with IoT. I talked about, a consensus mechanism for mobile systems. I talked about incorporating them into pub/sub brokers, and finally paying for IoT data. Next, I'm going to turn to a different area, which is dispersed computing. And here I'm going to talk about three case studies that are all kind of very closely related to each other. We started working in this area in, I think, about 2017 through a project that was funded by DARPA on dispersed computing. That's sort of how we got into this field. But we're seeing that it's a very interesting direction with lots of open questions. So hopefully I can give you a flavor of that. So the dispersed computing problem I can explain through an architecture of a system we developed called Jupyter, for orchestrating the scheduling of dispersed computing. The idea is that you have some large application, and this could be some machine learning processing of your IoT data, for example, and it's described as a task graph, a directed acyclic graph. Typically, the tasks represent computations, and arrows between tasks imply that you must finish the previous task before the next task can get started. And if a task has multiple parents, like all of them should finish and send their data before the next task can start. And you want to place these tasks atomically on different compute nodes that are dispersed geographically, typically. Now, they're not all typically in the same data center. They might be on, in a regional IoT deployment, might be city scale, might even be quite large, depending on the use case. But in general, you're given a network of computers, you're given a task graph, and you're asked, how should I place the nodes from my task graph onto these machines so that I can compute as quickly as possible? This is something called makespan, or as fast as possible in terms of the throughput of producing outputs, or minimizing some other cost metric, and so on. So I have different optimization objectives over that placement of task nodes to the compute nodes. So Jupyter, which we developed, essentially automates that process. It's built out using Python and Kubernetes and containers. So the tasks themselves are containers, and Kubernetes is typically used for container orchestration. But Kubernetes out of the box doesn't support taking into account the network conditions in doing the scheduling. So it doesn't know that there are dependencies between tasks, and that the task data between tasks has to traverse particular network edges. So this is the part that Jupyter needs to kind of provide, is optimize the placement, taking into account not only the compute requirements of the task, but also the communication requirements between the tasks and the available bandwidth on the network nodes. So we have this as an open source orchestrator. We've worked on it at very large scales, like 500 compute nodes, 800 plus task graphs, and very different test beds, both within and outside USC. So the system itself, at the core of it, you give it as an input the application and its description as a task graph, and what is each task's requirement in terms of how much work it has to do, what kind of work it has to do, maybe even does it need a GPU, how much memory it needs, and so on. And then on the edges, you're given some description of how much data does that task generate. We generally work with a deterministic description, but some of our ongoing work is looking at stochastic description. So the amount of data a task generates might be input dependent, might be stochastic, might be a random distribution. And then you are given some information about the compute network itself that could be dynamic and changing over time. So this is what kind of compute CPU availability I have, what kind of GPU availability I have at each node, what kind of network conditions are present, what's the bandwidth, how long will it take me to transfer data between point A to point B in the network right now, and so on. And so the Jupyter system collects this information about the application and the compute nodes. It actually runs an execution profiler to understand how long it takes to run task nodes on compute nodes. It keeps track of the current available resources from a compute resource perspective, as well as a network resource perspective. And then it has essentially a module where you can plug in different algorithms, whether they're centralized or decentralized, to actually do the scheduling of the task to the compute node that optimizes some given metric. And then finally, once you've figured out the schedule, there's a dispatcher which makes sure that the appropriate containers are available to run on the appropriate allocated task nodes. So this is kind of dispersed computing in a kind of at a high level. The system was implemented, as I mentioned, integrated with Kubernetes, and all of those different profilers and mappers and execution systems are all implemented themselves as containers within each kubelet. So the core scheduling problem in dispersed computing, as I said, you're given a task graph, you're given a compute network. We want to find a schedule of which task runs on which node, and depending on the speed of those nodes, depending on the amount of data you want to transfer and the network data rate of those links, there will be a certain total time taken to process that task graph, and that's often used as a metric. It's called makespan. A different metric might be if I'm going to run inputs repeatedly through this task graph. Imagine it's an ML pipeline and I keep feeding it new images or new data. I want to maximize the number of, let's say, images per second that it processes as a pipeline, then a better metric would be throughput. And there I'm interested basically in minimizing the bottleneck placement of computation or communication. So the algorithm's job is basically do that optimization. There's a very well-known algorithm that in fact goes back to the world of grid computing. And back then they were looking at mostly homogeneous compute nodes and static networks. With dispersed computing, if you want to apply it to edge computing and the Internet of Things, we're looking at more heterogeneity in the compute nodes, right? Some nodes will have GPUs and CPUs. The capability will be different at the edge versus in the cloud. The communication network, the wireless network, is going to be dynamic. It's going to, be time varying. And you can think of what Heft does in such a setting as a generalization of a lot of work on mobile offloading, right? So in the world of mobile computation, you think about, should I run my application on my device or, offload part of it to the server? That's like running a very simplified version of this problem where the task graph just has two components in it. Then compute network is just two nodes, your mobile device and the cloud. We're taking that problem and saying, let's look at the generalization of it, where the application is some arbitrary task graph and the compute network is some arbitrary collection of nodes separated with time varying links. We also came up with a distributed protocol for scheduling called Wave, which essentially starts with the top of the DAG, finds a place to schedule them, and those nodes that are scheduling, a particular task are then responsible for running an election and deciding who is in charge of placing each of the children task nodes. And wherever the children task nodes get placed, those nodes are responsible for the next generation and so on. And you can basically allow the scheduling to unravel in a wave through the network using just local information. And we showed that this sort of distributed wave system does better and better in terms of overhead of collecting the network state and doing the allocation as the scale of the compute network gets larger and larger. So while initially the mean make span for wave is, for example, this thing we're calling, let's say, greedy wave, is about 154 compared to 102 for Heft, which is a centralized scheduler. By the time we scale up the network to much larger values, you can see that the wave performance is about 97 versus Heft 136. So you're getting better performance with a distributed scheduler the larger your compute network. Another question we asked is, how long does it take to actually produce the schedule? We have algorithms like Heft that have been around for a long time. Can we improve on them using modern ML techniques? And our contribution here was to use a graph convolutional network to train on the outputs of a traditional scheduling algorithm and show that we can produce schedules that are competitive in terms of quality, but actually produce them a lot faster, because inference on an ML model is a lot faster than actually running through the whole heuristic scheduler that's out there. So the way this particular GCN scheduler works, it takes the two types of graphs in this problem, the task graph, which says what computations I need to do in what order and what is their data dependency, and it takes the compute network that I have and the information about how fast the compute nodes are and how fast the links are, and it combines them into a unified representation, which is an input graph where the nodes are tasks, the edges are between the tasks just as they are in the task graph, but there's kind of a vector of features at each task node that represents how fast it would run on each of the compute nodes. And there's a vector of features on the edges that represents how long it would take to communicate that data on different edges on the network. And with the sort of unified single input graph representation, we can train a graph convolutional network to essentially do a node classification task where we want to say for each task which compute node it should run on. So that's kind of the output of the GCN is for each task node label that says which node should you run it on in the given compute network. So we would train it on some example data that's coming from a traditional teacher algorithm, as we call it, a heuristic like Heft. But then the output, once it's trained, would intuitively be a lot faster with this approach. We did that, and our experiments showed that indeed we're able to train the GCN scheduler to produce outputs whose make span is comparable, in some cases even better than the teacher algorithm, although that wasn't really the main focus. the bigger focus was on the runtime, and we showed that the time it takes the GCN scheduler to find a schedule. So if you look in the bottom left box, for Heft, when it's on the order of, let's say, 0.6 seconds for a 20 task node graph to as much as thousands of seconds as that graph scales up, GCN scheduler stays and is able to kind of produce outputs more or less at a constant time that is scaling really, much more gracefully and is in the milliseconds time scale. So we're talking about orders of magnitude faster scheduling using a GCN scheduler than a traditional approach. And especially as the task graphs get larger, your compute networks get larger, this is clearly the right approach for doing this. And the benefit of this is in a IoT setting where your network is dynamic, your applications might be changing over time, your nodes might be mobile, so the network is, the structure of it keeps changing. You may need to rerun your task schedules over and over again. And the quicker it is to recompute a new schedule, in this case, in the order of milliseconds, you can respond at a time scale that is keeping up with the pace of changes in the network. So given that you can reschedule so fast, you can actually run this GCN scheduler on mobile networks. So we actually did some experiments with a collection of robots where as they move around, the network conditions are changing dynamically, and the GCN scheduler is able to adapt to the current network conditions in the order of milliseconds, find and recompute a new schedule, and launch it onto the nodes of the network, taking into account the current network conditions. And we showed that this is actually very uh, fast and competitive to, and much better than having a static schedule or trying to recompute with global knowledge. We have taken a lot of the literature that's out there on scheduling algorithms. I mentioned Heft. That's actually a very well-known algorithm, but there are dozens of others in the literature. So we've actually created an open source library for task graph scheduling algorithms called Saga. And currently it has about, probably a little bit more since I had the slide put up, but about 20-ish algorithms implemented and a number of benchmark problems that they can be applied to evaluate and compare the different protocols to each other. One interesting thing we found as we were implementing all these different existing heuristics, a lot of them come from the world of grid computing and high performance computing systems. One interesting thing we found is that a number of them belong to a family of algorithms called list scheduling. And this family of algorithms has kind of a set of dimensions. There's about 5 different dimensions that they differ in. So, for example, Heft, which I mentioned, uses a particular priority function, a particular comparison function called earliest finish time. It uses a particular way of doing insert only instead of append only scheduling. It doesn't make any reservations on a critical path, and it doesn't take into account something called suffrage in deciding which task to place on which node. A different heuristic that we saw in the literature called CPOP has a different set of choices it makes on these dimensions. But what's interesting is that while we found about 12 or so algorithms that are list scheduling algorithms described in the literature, when we look at it this way and you think about combinatorially every combination of these components, you actually end up with a larger parametrized set of 72 possible scheduling algorithms. You actually come up with new algorithms that haven't even been described in the literature before. So we took these 72 different possible scheduling algorithms and ran them over 20 different data sets to kind of understand which algorithms do well in which setting, and are able to kind of compare them on the basis of runtime as well as the solution quality. And we show that we say that a scheduler is Pareto optimal if for at least one data set it is better than any other algorithm in terms of there's no algorithm that has better both make span ratio and runtime. So if you kind of use that as a definition, we find there's a total of 24 of these schedulers are Pareto optimal on at least one data set. And what's interesting is that 20 of these 24 Pareto optimal schedulers were never studied before, were not described in the literature at all. So it kind of came up with a really rich set of new algorithms for the same problem. And the reason you need different algorithms for different data sets and problems here is that it's inherently an NP-hard problem. There isn't kind of a one algorithm that's going to do well across all settings. And so it's kind of a nice result of this work that we're able to discover new algorithms that show good performance on many data sets. So yeah, I'll stop here. Hopefully, it gave you a flavor of these two different types of computing paradigms: decentralized, which is really more about blockchain and trust and integrity and incorporating monetary value, as well as dispersed computing, which is more about taking complex applications, breaking them down, scheduling them on networks that are heterogeneous and dynamic. And I think in both of these areas, there's lots of open questions, lots of interesting directions to pursue. And I hope there's some interesting ideas that people take away from this talk and want to dig further. For all of the topics that I mentioned, we do have publications that are in these slides. I'll make them available to me to post at a suitable place if needed. And I hope that, yeah, I can take any questions that you may have about it. And I hope that this has been a helpful presentation. Thank you.
Thanks so much, Bhaskar, for the wonderful talk. Let's open the floor for the questions. Any question from the audience? Let me see if any question for the speaker. I can start with some questions. So, yeah, I think this GCN scheduler is quite interesting. Normally any AI or machine learning based scheduler requires training, I believe. But in this decentralized setting where you also mentioned about the nodes might be mobile, might be come and go. So in other words, the structure and the computational topology can be dynamic over time. So does that mean I have to retrain the scheduler given that the structure or topology has been changed over time? I do see the advantage of this the scheduler because of the superior inference time, right? Because when it's when
Training, yeah, it's just a matter of
goes
running
up.
through the, yeah. So no, that's a very good question. So what we do is we actually during training expose it to very different network topologies. So the training itself, the data set is very diverse. So you are seeing different link bandwidths, some nodes not being in reach. And you'll see even for the task, some variation of what the task graph looks like as part of the training. So you can make your training data set quite rich and diverse. And of course, like with any ML model, right, it's only as good as the type of data that you have seen. So there's a little bit of a trade-off in that the more data you have from either historical network configurations or from simulation, the better trained the model would be. But then, of course, you also need more time for training and more resources for training and a larger network to train and so on. So all of those, traditional trade-offs for ML systems apply here. So you would need to, if you have a very large network, more complex set of things you want to deal with, a much larger data set, you'll need more compute cycles for training. The model itself will be needing to have more parameters and so on. So all of that is still true. If you do want to do something where you retrain when new kind of data becomes available, again, the sort of standard art of ML retraining applies, right? When is the right time? Because the current system no longer looks like what you optimized for is a trigger to retrain the system and so on. But yeah, I think all of those are still true here.
Yeah, I think kind of a follow-up question on this is that I think the performance in terms of the scaling is superb. One of the reasons I can imagine is that it's like any other like a graphic models where you learn an embedding that basically is kind of like a compact dimension, so it's easier
Representation
to
of what's going
search.
on.
Yeah,
Mhm,
and then
mhm.
you can quickly indexing to the right downstream text, and then you can do a very quick inferences. Well, but it's also very hard in terms of training. So I'm just kind of
Yeah.
curious, like, um, you do you have some, kind of sampling technique? Because when the topology scales up, they're like, can be
Mhm,
millions of
mhm.
nodes. Um, you know,
What can
but
you do to, yeah.
yeah.
No, that's a very good question. So the training methodology we use actually uses relatively small um, task graphs to train with, but then we actually evaluate them on larger task graphs. And the system is fairly robust to that because it depends a little bit on the complexity of the model itself. But the GCN, if it only has k layers, you're effectively only seeing data from nodes that are k hops away, effectively. And so if you're training on data with a relatively smaller task graph, because in this graph, that's, the nodes are the tasks, you could still learn enough to get good performance on a larger task graph, because ultimately you only see so far into the larger network when you're doing the output. Which probably means that there could be problem instances where you're not doing as well because you only see so far, right? Unless you increase the complexity of the model, which increases the complexity of the training and so on. So there's some trade-offs there to investigate. But he also brought up another, and this is related, which is just in general a study that shows how does training time scale with the scale and complexity of the problem, and are there new techniques for sampling and if other efficient training that could bring down that to make it scale even better. I think that would be a great, yeah, direction for new research.
Um, Great. Any other question from the audience? Well, if no, I have another question. So, everybody now is talking about large language models, and these gigantic models. For those models, like they follow something they call scaling law, where you add more parameters, the performance will scale up. And I'm just curious because the scaling law tells us a pretty clear message is that the larger the model is, the better the performance. So people will, if we wanted to get a better performance, I need to get a larger model. And in that sense, seems like this larger model can only be hosted in the cloud or centralized place. I'm just
Mm,
curious to see opportunities for example, decentralized and dispersed computing, where how 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 these decentralized disparate computing paradigm gonna shift when we are dealing with this gigantic large models that seems to me can only can only work in a centralized or in a centralized place because it's so big and it's so computational consuming, where only the cloud server can take care of the workloads.
mm. Yeah, this is a fascinating question. So I think there's sort of two ways in which that whole conversation relates to dispersed computing. One is um, you can take that task graph that I described and use that approach to model for certain applications an agentic workflow where these tasks are basically agents getting some input from other agents, doing some processing, sending that input to other agents, and so on. Depending again on the application, each agent might be focused on doing one task really well rather than a general purpose LLM, right? So there is a school of thought that says that if you are really only going to do one task really well, the smaller agent model could be fine-tuned, smaller size model. And so a task graph that just consists of the smaller, well-trained model to do individual tasks put together as a pipeline might perform really well for a very complex task compared to a single large model hosted on a server somewhere. So I think that's one way in which the dispersed computing framework might help think about how to decompose the larger system into smaller pieces, just forcing you to think about it as a data flow system. and then on top of it help you say, well, even as I decompose it, maybe some of these models could be the Microsoft Phi 3, it could only be, you know, 1 billion parameters. Some of these other ones are complex enough tasks that I need 100 billion parameter model and so on. And just like in this dispersed computing, the tasks have different levels of complexity. Some of them need to do less, some of them need to do more. And on the compute network that I have, I may have some nodes with my, you know, A100, H100 GPUs. I may have others that are just simple laptops. Some of them are just Raspberry Pi or whatever. And so then I can think and optimize what model can run where on what resource that's available, and possibly even across a network, right? So I think this dispersed computing actually gives you a nice formal and structured way to think about decomposing a large language model, think about how to place the, you know, elements of the model in a given system. So I think, yeah, that's a fascinating direction to explore, particularly if you can get, you know, hands-on good applications where this decomposition can be evaluated. The other thing that it makes me think about, which we have explored in the past, but not with large language models, is what if I start with my overall graph that is the large language model's, you know, underlying neural network, and I ask, how can I just take the large language model itself and decompose it into subnodes where the outputs of computations here get sent to another one and so on. And actually, if you look at, you know, PyTorch actually produces an intermediate representation for any model that is itself a directed acyclic graph.
That's right.
And so in theory, you could take that and plop it
Yeah.
down on different nodes, just like, you know, so you start with the task graph and you say, here's my compute network, and say, how do I break down this larger processing itself? Now, the tricky thing there, I think, is that the many of the layers might be dense layers that want everything to talk to everything else, which may kind of defeat the purpose a bit, in the sense that you're not able to kind of have like multiple children of a node. Everything is just another node, and all of that data has to be shipped over and so on. But to me, that's also an interesting, you know, ML optimization or ML systems question, which is, can I prune the underlying network or the architecture in ways that are well suited to the networks I might have available, or that create decompositions that are easy to split across nodes in a distributed or network setting. So that could be very interesting, kind of joint ML model optimization with the dispersed computing type of question. And this is still inference, but just a larger model. And then finally, I guess, now that I think about it, maybe there's also some interesting question of, can I speed up training by running it over a network? We haven't worked on that much. We thought about it a little bit because it's a little bit more complex, since you have to do forward and backward passes through the computation. But if and you're doing it in repeated cycles, but you know, if you did a good placement of this model across a compute network in ways that maximize, say, the throughput of the processing, you might actually get a good placement that speeds up training as well. So, you know, how to do that. And maybe if you have different energy costs at different nodes and you want to minimize the energy cost, that could also be something to be explored. Yeah, but it's like I think a fascinating area to really take this dispersed computing view of distributing large models and ask about how to train them better, how to do inference with them better. I think, yeah, this could be really a rich area for exploration.
Yeah, I think I totally agree with that. I think that, you know, the large language model, or these you know, AI agents, gonna dominate the whole world. And I was just thinking of how we can leverage that in networking research. For example, dispersed computing, where, you know, the DAG, every node in the DAG can be a agent itself, or can be part of the agent. So we can distribute the workloads across the whole network and make it everything more efficient. Yeah, and also, you know, you can apply this to blockchain and to many other networked applications. And you know, I'm
Yeah.
assuming in the future, like, everything gonna be agent based. So, you know, how to deploy the agents and how to allocate or decompose the whole problem into different agents can be yeah, can be very interesting in the near future.
Yeah, I see a question in the chat from Fatime.
Oh yeah.
Um,
Uh, Yeah, as a follow-up question, how would you provide privacy in that case? In the case of
Distributing a large model across, different. Yeah, this is a very good question, right? So I was just thinking like a nice use case of all this. If you don't want a single cloud provider to host the model, you have a bunch of people with their own machines to be able to help train and serve. But now you have some privacy issues. It's crossing different organizations. You may or may not trust them with the raw data you're using for training. Yeah, I think short answer I can give is I haven't thought about it. This is a very good question. I wonder whether some of the federated learning approaches apply here. But does it, that might make sense actually for the agentic framework where different agents need different types of data to train. But again, if you don't trust them with the data that you want them to train on at the location you want them to train on, then I'm not sure what you can do. Does it come down to using some trusted execution environments? Can we leverage? I have a lot of interest going back to decentralized computing. One of the big advances there has been in what's called zero knowledge proofs,
exactly.
which let you basically give someone else the task of doing a computation and then verifying that they did it correctly. So, and privately. So they don't have to reveal what computation they did, but they just have to prove that they did the computation. So I imagine, there could be some interesting ways to leverage advances in, it's called, actually, there's a growing field called ZKML, zero knowledge machine learning. And I wonder whether that could also help with addressing these questions. But I think, Fatima, you're asking a wonderful question. I think this is, a good research area to kind of explore, like what would be good mechanisms to also give privacy while distributing large ML models, both inference and training.
Wonderful. Great. Okay. Thanks, Fatima. So, any other question from the audience? Okay, if no, we can probably conclude today's talk. And thanks. Let's thank again Professor Krishnamacharya for the wonderful talk. Yeah, thank you for taking the time and giving us the wonderful talk and the great discussion after the talk. So thank you, everybody. We'll see you guys next time then. Thank you.
Thank you. Thank you all. Bye.
Bye.